So yeah. Okay. So when you see this, this list of symbols being printed across the page, you can ask what is it. So you would say just some garbage, some nonsensical mumbo jumbo, but it's actually an encrypted message. Okay, and you don't know what it means, but if you knew the encryption key, you can just read it. So, to me, this is what theoretical physics is like. So, we all have different ways. So, I mean, the beauty of research is that everybody looks at things in their own way. And that's what makes it very interesting. And if you ask theorists, what is theoretical physics about, you'll hear all different answers. As some people would think that the more complicated or mathematical the theory is, the better. From my perspective, what theorists do is the following. Nature presents sets of facts to us. And at first they seem kind of unrelated, mysterious. And you don't know, you don't know what nature is trying to tell us through those facts. But then at some point you figure out the underlying principle. And once you look at things through that, suddenly everything makes sense. It all fits together. You can see that everything is part of this beautiful picture, And so theory is that kind of brings, it's the idea, it's the encryption key that gives coherence to a lot of different experimental fields. So today what I'm going to tell you about is this thing, Nick already mentioned. So if you take electrons in 2 dimensions and expose them to a strong magnetic field, suddenly it transports you into an incredible world where we have exotic particles that cannot exist in 3-dimensional world by the laws of quantum mechanics. And many of these things are so strange that you would not believe they could happen except that they really happen here. And in particular, we'll see that a lot of the experimental facts are described in terms of composite fermions, which I have shown here pictorially. And I have also, so it's one of the things that I have come to appreciate is how fortunate we are to be living in this age of science. So if you think back, let's say 400 years ago, when we didn't have Newton's laws, people had no idea what was happening. Things are falling down. There are, things thrown down, planets going around each other. Then Newton said, okay, they are all connected. They're all following the same equation. And then about 100 years ago, we had no idea about quantum mechanics, so we didn't know what was happening. And suddenly now we are in a stage where, just within a span of 300-400 years, which is like blip in a historical sense, in this little planet, this little human race has figured out how the universe started. What is the equation that everything is following? It's absolutely amazing. So, it's already 2026, but last year was the International Year of Quantum Science and Technology to commemorate 100 years of the discovery of quantum mechanics. And it's something that still continues to work and surprise us. Okay, so what I'm going to tell you is a story with many twists and turns. And that's true for every branch of science. Take anything, you find that just when we think we understand everything, nature throws a curveball and you say, how did that happen? You understand that, and then suddenly something else comes about. So there are, it's like, um, we could not have written a better detective story. You know, it's absolutely, uh, uh, captures you. And so I'll tell you how the fractal Hall effect story unfolded slowly, and how at first you might think that it's an extremely hard, maybe impossible problem to solve. How one came up with the idea of composite fermions, and then of course there are others, exotic particles that have been predicted to exist, like anions, Majoranas. And so today will be just very simple introduction. Tomorrow I hope to get time to talk about more recent stuff. Okay, so let's begin with the Hall effect. It was discovered by Edwin Hall. So he was a student at Johns Hopkins. I was just talking to another graduate student from Johns Hopkins, and he was trying to understand how Ohm's law behaves in the presence of a magnetic field. And he found that the resistance is roughly constant. But then he noticed that there is also a potential drop across the current path. So he defined a new resistance, which we now call the Hall resistance. So it's Hall voltage divided by the current. And he found that it rises linearly as a function of the magnetic field. So, I recently, a couple of years ago, I went to Johns Hopkins University, and I learned that Hall was an extremely lucky guy for two reasons. One was his advisor was somebody named Roland, who was, a person highly reputed at that time, very well known. He said, "Oh, this is just a small effect, Why don't you publish it in your own name?" So that's how Hall published the paper in his own name, and it got to be named the Hall effect. But that was not it. Then, we have his name carries into integer quantum Hall effect, fractional quantum Hall effect, anomalous quantum Hall effect, fractional anomalous quantum Hall effect, and so on. And all of these had nothing to do with it. So, okay, so it remained like this for about a century. And, there was this twist. I mean, you all know. And this twist occurred just at about the time when I started my PhD work. So I came to US in 1981. And in 1980, unbeknownst to me at that time, there was the discovery of the integer quantum Hall effect. So what was it that made the discovery possible at that time? Well, this was the time when two-dimensional electron systems had become available. So at that time, the idea was that you take a thin, piece of semiconductor and sandwich it between two other semiconductors, make a quantum well. Electrons can move only, across, in two dimensions, but not in the perpendicular dimension. Of course, now we know there are other ways to get two-dimensional electron systems like graphene. So Klaus von Klitzing, he said, let me measure the Hall effect in two dimensions. So he started, initially it looks very similar to what one expects. But then he found that as he went to higher magnetic fields, the Hall resistance took some special values. So it jumps from one value to another. And this was rather surprising. And at the same time, he found that the ordinary resistance essentially vanishes. So it's not zero, it's exponentially small. But that's what this looks like. So this now this says that the Hall resistance is quantized. But the thing that made it really, really interesting was Claus's observation that the value of the Hall resistance on these plateaus, as they are called, is independent of all details. So now if you measure resistance, the resistance depends upon how long the wire is, what the wire is made of, and so on. But here, no matter which two-dimensional system you take, whether it's a millimeter wide or a mile wide, you get the same value of the Hall resistance. So this was very surprising, and it's called the integer quantum Hall effect. And Claus won the Nobel Prize for this very soon in 1985. This was discovered in 1980. Okay, so why is this taking place? Well, let's minimize energy. So I'll think of zero temperature. So there are two energies. There is kinetic energy, interaction energy. So let's first focus on the kinetic energy. Now, one of the magics of quantum mechanics is that in a magnetic field, if an electron is in two dimensions, then its kinetic energy is quantized. It can just take some special values. These are called Landau levels. And if you minimize the kinetic energy, then you say, okay, we are going to put electrons in the lowest Landau level, but there is only a finite amount of space in the lowest Landau level. So once you fill that, you have to fill second and so on. But you try to occupy the lowest available Landau levels, and that's what the system. That's what the lowest energy state looks like, typically. So here I have used the idea that in each Landau level, there is a finite amount of space. This is called the degeneracy, and it's given by this expression here. And the number of filled Landau levels is called the filling factor. So here the filling factor is somewhere between 2 and 3. And this will play, the concept of filling factor will play a role as we go on. So this is what the situation looks like. And here, if you put the electron, you could have put the electron here or here. So there's some, freedom that we are still left with. There are lots of different states which have the same energy. But when the filling factor is an integer, like this, there's something special. So we now know the ground state exactly. So I call this phi 1 or phi 2. These are just later determinant wave functions of these ground states. And moreover, there is a gap to excitations. So it's this properties that leads to the phenomenon of the integer quantum Hall. Okay, so the fact that we have a unique ground state and there is a gap to excitations. Now let me also say here parenthetically that disorder also plays a role, somewhat surprisingly, in establishing plateaus, but that's something that I won't go into this. Okay, so why is integer quantum Hall effect happening? Because we have states like this. So that's the picture of integer Hall effect. Now, just a year after I joined my PhD, there was another twist. So, you can imagine right after, like in 1981, people thought, we understand the integer Hall effect. Beautiful phenomenon, chapter closed. But no, there was another surprise, and Sui, Stormer, and Gassard went to higher magnetic fields, better quality samples, and they saw a quantized value where we have this fraction 1/3 rather than an integer. And soon following that, Bob Laughlin had a brilliant ansatz for a wave function for the ground state at filling factor 1/3. So he said, okay, it's interactions have to play some role. That's and he wrote a wave function where you can see that electrons are explicitly keeping away from one another. Okay. So again, in 1982, it seemed like story complete. 1/3 was seen, 1/3 was explained. But it turns out that the story was not over yet. And in fact, it was in some sense only beginning. So as experimentalists improved the sample quality and, went to higher magnetic fields, lower temperatures, they saw an incredibly rich structure like this. So there are lots of, this is integer, but there are lots of these quantized values. They're all labeled by fractions like 1/3, 2/5, 3/7, and so on. Whenever you see a plateau here in the Hall resistance, you see a minimum in the longitudinal resistance. So, if I think this is still, this is not the latest, but it's still from 20 years ago, but you can see incredible amount of structure here. So it's a stunning manifestation of quantum mechanics at macroscopic scales. I often make the claim that this is the most beautiful single trace in physics. Okay, so and I challenge the audience. So it just single trace. All one is doing is measuring the resistance as a function of the magnetic field, and you see all the structures. So once somebody said, "Oh, how about this detection of gravity waves when two black holes, collided?" I said, "Well, this looks better, but if that's the competition, we are not complaining." That's sometimes people say, "Why is it beautiful?" And in fact, at this time, we cannot see it, but we'll see that this all can be explained from one principle, and that's what really makes it beautiful. Okay, so again, thinking about my own story. I was not working in fractional Hall effect. I was curious about it. And in 1986 or 87, there was the discovery of high temperature superconductivity, and I cannot convey to you the kind of excitement it produced. These are some pictures from a meeting, a March meeting in 1987, which was called the Woodstock of physics. So tremendous excitement. So a lot of theorists, they went to they jumped onto the high temperature superconductivity problem. But let me tell you the problem. Okay, so let me introduce to you the minimal model that we would like to solve for the problem of two-dimensional electrons in the lowest lambda level. So minimal, okay, so if you write everything, then this is kinetic energy, this is interaction energy, Zeeman energy disorder. I'm going to, being a theorist, assume the limit where the magnetic field goes to infinity and there is no disorder. So if magnetic field is very large, electrons all point in the favorable spin direction, so I can forget about the Zeeman energy. This energy, so when B goes to infinity, I have to put all electrons in the lowest lambda level, so I can forget about this. And the Hamiltonian, minimal Hamiltonian, has this rather simple form. It's just the Coulomb energy of electrons in the lowest lambda level. And notice that there are no parameters in this problem. There is no mass, no kinetic energy. We just have electrons interacting with the Coulomb repulsion. So, and we would like to solve this problem as a function of the filling factor. We want to understand what the underlying physics is. Of course, we would like to make predictions, calculate, we would like to understand. So the reason it may at first seem impossible is the following. So, first of all, I mean, we all have heard of flat bands, So the Landau levels were the original flat bands, and I think they're still the flattest amongst all. Once you have a flat band, which means the kinetic energy is the same, the interaction energy is the only energy scale in the problem. The exact solution to the Hamiltonian that I wrote in the previous slide is not known. And of course, that does not stop condensed matter physicists from making progress, So in condensed matter, we never know exact solution. But nonetheless, we have made tremendous progress because we do perturbative schemes. I mean, we have tremendously, and I have to say, the fact that in condensed matter physics, we understand so many things so well is itself rather amazing, because these are extremely complicated systems of Avogadro number of particles that are all interacting with one another, and still we understand. But here, we have no small parameters, so we cannot do any perturbation theory. And if you count how many degenerate ground states is, you get some ridiculously large number of states. So, not knowing where even to begin, you say, how do I deal with this problem? Okay. So if you did not have experiments, there's no way one would have made any progress in the understanding of this. Okay. So as I told you, I was not working in fractional Hall effect. There was this excitement of superconductivity. But there was one thing that I had noticed, like there are students here, as students we say, what is physics about? So you learn a chapter, then there are problems at the back. And you say, okay, I have to solve problems. And you say, okay, theoretical physics has to do with solving problems. But that's not really true. The theoretical physics is to understand what's the right questions. We have to figure out what is the question that we would like to answer. So, asking the right question at the right time has a lot of power. Okay. In fact, if you have to work on the question, and if you ask the right question, it often has the answer in it. So, what's the question here? So, I had noticed that everybody knew actually that in a practical sense, integer and fractional Hall effects, they look identical. So, if I remove the numbers from here, one would be hard placed to say whether this is integer or fraction. They are all identical. So you say, if that's true, then there must be some way to unify these two effects. Well, let's work on the question, what does that mean? What does it mean, unify the two effects? Well, this has to mean that we have to understand the fractional Hall effect as some kind of integer quantum Hall effect. Let's think a little more about this. What does that mean? That means there must be some emergent fermions. So, integer quantum Hall effect was an effect of non-interacting electrons. So, there must be some other objects which are essentially non-interacting, the integer quantum Hall effects of which would produce the fractional Hall effect. Okay. So, what are those weakly interacting objects? So, I kind of had, in some vague sense, this kind of thought, but I didn't know what to do with this until suddenly I had a little bit of insight. So this was when I was a postdoc at Yale, and I realized that if I introduce these objects, these are called composite fermions. A composite fermion is the bound state of an electron and an even number of quantized vortices. And in practice, one can think of them pictorially as the bound state of an electron and an even number of magnetic flux quanta as shown here. So I realized that if I introduce these objects, then I can map integer and fractional. So I can map fractional Hall effect into integer Hall effect of these objects. So let's see how that works. So first of all, the pictorial view. So it's, at some level to convey the physics is almost straightforward. So I say electrons are strongly interacting, exposed to a strong magnetic field, but each electron captures an even number of flux quanta of this magnetic field to turn into a composite fermion, and composite fermions themselves interact very weakly. So, the key here is that composite fermions now do not see the magnetic field that they have captured. So they see the residual magnetic field, and just looking at this picture, that's equal to the external field minus an even number of flux quanta removed per particle. So now we'll boldly go ahead and say we'll treat composite fermions as good old garden variety fermions, define a filling factor for them. And so the composite fermion filling factor and electron filling factor are related by this expression. Okay. The composite fermion lambda levels are often called lambda levels, just to make sure that there is no confusion in the terminology. So in particular, when composite fermions fill an integer number of lambda levels k, then the electron filling factor is given by the expression here. Okay, so that's the qualitative physics, and lots of experimentalists, just saying this, this by itself, as we'll see, explains lots of experimental phenomenology. But one can also go ahead and try to construct a wave functions for these states. So now we have established mapping between non-interacting particles at some filling factor and interacting at some other filling factor. Let's work on it. So so I have non-interacting particles at some filling factor nu star. I should have called it nu CF. Okay, so it's so think of this as nu CF. It's composite fermion filling factor. So there we know all solutions. It's non-interacting problem. I know ground state, excited states, and so on. So I can list all of those. Then we are going to attach Bodice flux quanta through multiplication by this factor, and we'll say that. So I would like to identify this as the wave function of my strongly correlated electron system. There is a little problem here, which is that this wave function is not in the lowest lambda level, so I'm going to project it into the lowest lambda level by hand and identify it as an ansatz wave function for interacting electrons in the lowest lambda level at filling factor given by this formula. So notice that, we are writing a single equation that is that provides ansatz wave functions for all eigenstates at arbitrary filling factors, and in particular at some special filling factors where the nu star or nu CF is equal to P, we have a unique wave function for the ground state. So on the right hand side, there is no adjustable parameter. Okay. There is also a field theoretical method or more than one, I might say, to deal with this problem. So Professor Son will do this. We'll give some lectures about this, but there is this Chern-Haber's field theory. Just wanted to mention it, but I won't do anything else. Okay. So let me also point out that the composite fermion is actually a quantum mechanical, topological, and collective entity. Why so? Because a vortex is actually a an emergent structure in which all particles participate, all electrons participate. So it's a collective object. The vortex is also quantum mechanical because it carries phases with it, and it's topological because if a particle goes around a vortex, it gives you a phase of 2 pi, independent of how it goes around. But if it does not go around, then you get a phase of 0. So therefore, a composite fermion is also a quantum mechanical, topological, and celestial particle. So one can ask the question, do composite fermions exist? And if they do, in what sense do they behave as particles? Now, of course, experiments have the final word on all theories. We have, as theorists, we would like to make predictions, hopefully non-trivial predictions, and also explain experimental facts. So what I'm going to show is that composite fermion theory actually explains lots of different types of experiments. It explains thousands of non-trivial facts, as we'll see, in a unified, natural, and unambiguous fashion. So in fact, once you think in terms of composite fermion, there are lots of phenomena that seem trivial, you say, of course. But if you go back and think about them in terms of electrons, then they're extremely non-trivial, Okay, so let's start with integer quantum Hall effect of composite fermions. So as I said earlier, if you start with these wave functions and, these filling factors, and ask what is the composite fermion filling factor, it's integer, or of course one could go the other way. And at these filling factors, these infinite choices that we had for the electrons suddenly disappear, and we get unique solutions when we look at the problem in terms of composite fermions. And it turns out that this correctly predicts almost all of the observed fractions. Not all, but almost all. You see these sequences of fractions that are coming here, they all follow this formula. So here we have a system described in terms of composite fermions carrying 2 flux quanta, here in terms of composite fermions carrying 4 flux quanta. In fact, I'll take this panel and redraw it here. And you can now see that the fractional Hall states here, they map into integers. So, 1/3 aligned with 1, 2/5 aligns with 2, and so on. So, if you measure magnetic fields from here, this looks just like the integer quantum Hall effect of some particles. So this was already like 20 years ago. 10 members of this sequence had been observed, and several members of higher order sequences. But more recently, as they have improved the sample quality even further, they see more and more of these, and they completely align with the expectation in terms of composite fermion. Okay? So this already is pretty remarkable. In fact, composite fermions carrying 6 and 8 flux quanta have also been observed, or there is evidence for that. So this is composite fermion carrying 6 flux quanta, and there are these minima. So here it turns out that the system is trying to become insulated as you lower the temperature, but so long as you can measure the resistance, you find that there are these minima, and they align very nicely with what you expect from fractional Hall effect. Of course, nothing special about gallium arsenide quantum wells. You could go to monolayer graphene, bilayer graphene, same fractions. Okay, so another rather remarkable prediction in those days was of a composite fermion metal. So This was by Halperin, Lee, and Reed. And I mean, so for any theory, you want to ask what happens in some extreme limit. Okay? And here you could say, well, what happens if I take the limit where P goes to infinity? At that point, the filling factor of electrons goes to half. And one of the puzzles had been, why is there no fractional Hall effect at filling factor half? Okay, this is the simplest filling factor after all. And once you look at the problem in terms of composite fermions, you notice that here the magnetic field seen by composite fermions is 0 because electrons kind of capture all of the flux coming as them. And therefore, the prediction was that composite fermions form a metal or a Fermi liquid here. So, there have been lots of beautiful experiments that have confirmed this. They have measured the Fermi wave vector. They have measured, all of the things we ascribe to Fermi liquids like Shumnikov, de Haas oscillations, and so on. And in my mind, it was this experiment. I mean, all this set of experiments or understanding was important because it says that composite fermions, in some sense, precede fractional Hall effect. So, just like electrons existed even before quantum Hall effect, composite fermions now exist outside of fractional Hall effect. Okay. And so this is in contrast to concepts like fractional charge and fractional statistics that follow because of the observation of the fractional Hall effect. Okay, so far what we have, just like we had the integer Hall effect, we have fractional Hall effect is understood like in these pictures, and we also have an understanding of the state at filling factor 1/2. Okay, so I think Horst had said enough, but see, let me say about this. So it's this was made by a professor who was a student of mine a long time ago, Kwan Park. He prepared this poster. So first of all, they made me look much younger. This was already 10 years ago. But they made me look much younger. So I look probably not much older than a K-pop artist. I think it's, Koreans are well known for cosmetic surgery, and they did some cosmetic surgery here on me to make me look much younger. But the thing I would like to show is that Kwan Park tried to explain the physics of composite fermions subliminally here. So if you look at the lower panels, you would see there are electrons which are interacting with one another and they are not happy. Okay. But then if you look at the upper panel, they have all captured 2 flux quanta and they are happily, flying into the skies like happy little angels. And the thing is, before every talk, I debate with myself, should I show this or not? Because I know that a year from now, if I ask you, what do you remember from this talk? If you remember anything, it would be this. And but then I say to myself, well, if you can remember anything, I would consider that as success. So that's one part. Okay, so how much time do I have?
But I think I would use answer as and to say, and to say, and to get, want to get, to get, then I have their time. So that 40,000 an hour.
Oh, okay.
But you can also start good.
Okay, so let me, I don't want to go too long. Let me just talk about, maybe 10-15 minutes.
Oh, the fucking
Okay.
it's open.
Okay. So, these things are already surprising, but to me, the most amazing thing about the scale is the following. So, now let's try to see in the most microscopic fashion whether to what extent this works. Okay, so what I'll do is, so we saw this equation earlier. We'll do two calculations. One is I will go on the computers, get exact eigenstates and eigenenergies by just a brute force diagonalization of the Coulomb interaction. Okay. The second calculation would be I will find the energy. So this already gives me a wave function, but I can calculate the energy from this. So these two are completely independent. We are going to put them on the same page and see how well they agree. And the two calculations are independent and neither of them makes any approximations. Okay. So this is an example. So let me take filling factor 3/7. This is exact diagonalization of the Coulomb problem. We have assumed that electrons move on the surface of a sphere. So this is a nice choice for the boundary conditions. And a magnetic field is produced by what you can imagine a magnetic monopole sitting at the center with the magnetic field coming out radially. The system has 18 particles, so it's fairly large. And let me also note that what we are seeing here is very, very low part of the spectrum. So we have zoomed into the, lowest region of the spectrum. And so because of the geometry, the relevant quantum number here is the total orbital angular momentum. So that's this axis, and at any angular momentum, if you go look here at the top, this is the total number of independent basis functions. So it's like 2.6 billion. So if I put the full spectrum, there are 2.6 billion tick marks in this tower. All of the structure you see is coming from interactions. So if you switch off the interactions, they all collapse into one energy. And it's just the fact that, you see there are these gaps opening that already tells you that there is something non-perturbative going on here. And needless to say, there is huge amount of information in these, because each eigenstate here, I know everything. So experiments give you one number, but here using this, we can calculate any correlation function, energies, gaps, etc. Okay, so what does the composite fermion theory say? Well, it says, this is 3/7, which maps into filling factor 3. So it would say this is 3 filled lambda levels of composite fermions, the wave function of which I know precisely, and I can evaluate it on the computer. So doing this kind of projection, it took us many years, maybe about 10 years to learn how to do it, but we can do it for very large systems now. And this set of states here, you say, okay, that's a particle hole pair excitation of composite fermion. So that's an exciton, you may say. And the wave function of this is also precisely known once you fix the angular momentum quantum number. So we say, okay, let's go ahead and calculate the energies of these. And we get the dots here. So almost exact agreement. So, in the beginning, I remember when we were doing 2/5 for 8 particles, and we found that the energy was almost exact and the overlap was like 99.9%. We said, how can it be? These wave functions are extremely complicated once you project them into the lowest lambda. So we never expected that. I thought, these wave functions would be in the right phase, qualitatively good, but we never expected such quantitative accuracy. And even now, people ask me, why are they so accurate quantitatively? I say, I don't know, but I will say I'm not complaining. One can ask, okay, how about these states? Well, so we say these states are two excitations of this type, So you take this basis, do a diagonalization within this basis, and you get these. So, we can construct states systematically, higher and higher energy excited state. And nothing special about 3/7. I can take 1/3. Similar level of agreement, I can take 2/5. I can take states in between. So this is somewhere between 1/3 and 2/5, these two. So this has, I haven't talked about quasi-particles, but this has 4 quasi-particles on top of 1/3. This has 6. And these are what composite fermion theory gives. And the blue dashes are the real, the exact eigenenergies. They continue to agree. So I have shown you energies, but one can just calculate overlaps. So for example, at 4 dynes, this is for 16 particles. And this is the exact energy, composite fermion state, overlap 99.51%. Okay. All right. So to me, this obviously could not be a coincidence. But it's still remarkable how well the theory works. So now one can ask, do the composite fermions do anything else? It turns out they do. So, as I said, there is experimental evidence for composite fermions carrying 2, 4, 6, and 8 flux quanta. And we have talked about integer quantum Hall effect of composite fermions. And we have talked about metal of composite fermions. But it turns out they do lots of other things. For example, there are stripes, crystals of composite fermions. They have a lot of physics that has to do with spin or Valley degree of freedom. There are composite fermions in bilayer states. They have their own fractional Hall effect. So their own fractional Hall effect shows states at fractions which are different from the sequences I had shown earlier. Now there is evidence for fractional Hall effect at several even denominator fractions, and they are understood in terms of quote unquote a superconductor or a paired state of composite fermions. And most recently, composite fermions have been seen in zero magnetic field in these fractional quantum anomalous Hall effect systems, either in twisted PMDs or multilayer graphene. Lots of different experiments have probed composite fermions in many different ways. So just to summarize, what have we accomplished? So prominent fractions have been predicted successfully. So notice that all these fractions are explained in the same fashion. Okay. So in one shot, so they are all unified. We have unified fractional and the integer Hall states, and also fractional Hall states and non-fractional Hall states. For example, the half-filled metal. Many other states, as I already mentioned, like superconductor stripes, crystals, etc., have been seen. Microscopic theories surprisingly accurate. A lot of the phenomenology can be explained without any detailed theory, but one can also do detailed. And let me just, I had stressed this earlier, but at ceiling factor 1/2, we have a fermacy of composite fermions. If you didn't have composite fermions, you think in terms of electrons, there's no way you could understand. So there is no kinetic energy in the problem. You say, how could you get something which has to do with kinetic energy? Another way to look at this is as follows. So suppose I'm good with computers, and I run my computer, produce thousands of eigenstates. Each eigenstate is a list of numbers. That's it's the projection of the eigenstate in different direction of the Hilbert space. So I have huge lists of numbers. But computer does not tell me how to think about those numbers and how to, and what the underlying physics is. So what we have figured out is that we can remove all those numbers and combine them into a single equation. Okay, so just by unpacking this equation, I can recalculate those numbers to a very good precision. Moreover, this equation tells me how to think about the physics, because when I look at this, I say, oh, this tells me that there are vortices bound to electrons. And then I say, okay, maybe I can think of them as particles moving in an effective magnetic field. Okay, so I think it's remarkable that this has become one of the best understood strongly correlated states in nature. And I again mentioned this most recent twist was observation of composite fermions, or these sequences in zero magnetic field. So so this is something I should say, if somebody had told me 5 years ago that fractionally quantized states will be seen in zero magnetic field, I would say no way. I would bet a year's salary. So I was so this was rather amazing. When I learned about this, Horst Stormer he is happily retired, and not keeping in touch with this. But I could not help myself. I sent him a message. I said, Horst, do you know that fractional Hall effect has been seen in zero magnetic field? He responded, he said, absolutely mind-boggling, weirder than we ever thought. So maybe with this, I'll close my talk. Thank you.